Have you ever stopped to think about the electricity that's all around us? I mean, it's invisible, it's silent, but it actually has a shape. A really specific, elegant, and incredibly important shape that's flowing through your home right this second. Okay, let's dive into this and really uncover the rhythm of our modern world. So, if you could actually see that electrical energy, what would it look like? Is it just some chaotic mess? A straight line? What is the fundamental pattern that's keeping our lights on and our devices charged up? It looks exactly like this smooth, predictable, totally continuous wave. This is the sine wave, and it is basically the heartbeat of our entire electrical grid. Now, yeah, there's a formal math definition. It's a curve that describes a smooth, repetitive oscillation, but for us, the most crucial thing to get is this. It's the shape of alternating current. AC power, and that's the juice that runs pretty much everything we plug into a wall.
Visit youtube.com/avidsystem and don't forget to subscribe.
But where does a shape this perfect even come from? It almost seems too clean, too designed, doesn't it? Well, the amazing thing is, its origin comes from one of the absolute simplest shapes in the entire universe. It all starts right here, with a simple circle. That's it. Nothing fancy. This is the engine that's going to build our wave. All right, now imagine a single point on the edge of that circle, just spinning around and around at a perfectly steady speed, kind of like a horse on a carousel, just going in a perfect loop. Now forget about whether it's moving left or right. We're only going to focus on one thing. Its height. How high is it from that center line? You can see it, right? It goes up to a maximum, back down through the middle, down to a minimum, and then right back where it started. So what if we take that journey and just unroll it? We plot that up and down motion against a timeline that's moving forward. As we do that, a very, very familiar pattern starts to take shape. And boom, there it is. The simple rotational motion of a point on a circle, when you track it over time, creates a perfect sine wave. And this is so cool because it's the direct link between mechanical rotation, like in a giant power plant generator, and the electrical wave it spits out. Okay, so now that we know where it comes from, let's kind of break this wave down. Let's look at its essential parts. There were just a few key terms we need to know so we can speak its language. First up is amplitude. Just think of this as the wave's strength, or its height. It's how high the wave gets from that center resting point. In electrical terms, you can think of amplitude as being related to the voltage. Next, we've got the period. This one is all about time. Specifically, it's how much time it takes for the wave to complete one full journey. From the starting point, up to the peak, down to the valley, and all the way back to the start again. And of course, closely related to period is frequency. So if the period is how long one cycle takes, frequency is how many of those cycles you can pack into a single second. And we measure this in a unit called Hertz, or Hz for short. And what's really cool is how these two things are perfect opposites. They're two sides of the same coin. Think about it. If you have a really long period, meaning each cycle takes forever, you'll have a very low frequency, right? You can't fit many in 1 second. But if you have a really short period, you get a super high frequency. They're just simple inverses of each other. So how do we talk about a specific point along the wave's path? Well, since the whole thing comes from a circle, it just makes sense that we use the language of rotation to describe it. We can measure our progress around the cycle in degrees, just like a circle. 0 degrees is the start, 90 is the very peak, 180 is when it crosses the middle again, and a full 360 degrees brings you all the way back to the beginning. Now, you might also see this other unit here called radians. Don't worry about the name, they both just measure the exact same thing, exactly where you are in the cycle. Okay, so a spinning circle makes a pretty wave. Why should you care? Because this isn't just some abstract idea in a math book. This wave is, and I mean this quite literally, what powers our entire civilization. This quote really says it all. From the moment that power is generated to the very second it enters your home, it's traveling in this shape. And why this shape? Because its smooth, gradual change is just incredibly efficient. It wastes less energy as heat, and it's much gentler on all the equipment, which makes it the absolute perfect way to send power over huge distances. And that wave isn't just random. It has a very specific frequency. Here in North America, that frequency is 60 hertz. Now think about that. That means the electricity flowing in your walls is completing 60 of those full cycles, just like the one we built, every single second. That's amazing. And this standard actually varies a little bit depending on where you are in the world. In Europe, the UK, and a lot of other places, they've standardized on a slightly slower 50 hertz. So the shape is exactly the same, but the rhythm is just a little bit different. So let's just end on this thought. We've seen how the simplest possible rotation creates the exact waveform for our entire power grid. But this wave also describes sound and light and even the orbits of planets. It really makes you wonder, doesn't it? What other parts of our universe are secretly dancing to the simple, elegant rhythm of the sine wave?
Thanks for watching.